So section 2.9, applied optimization. This is the focus of our class today, focus of our lesson today, okay? In the previous lesson, we used derivative to find maximum and minimum of some of the functions and equations. But remember, in most of the situation, we were given the function, the ready-made function. And then what we did is with the given function, then we find the derivative, we find the critical number, and then we test and check whether it is actually minimum or maximum. That's what we did. But if we think of the real world situation, the function doesn't come in that ready-made format, right? In the real world, there is a problem situation. There is some context, okay? There may be some data. And out of the data, out of the problem situation, you need to create those functions or equation, right? So that's the real world situation, actually real world problems. And something like, what is the largest volume of the package that the post office will accept? What is the quickest way to go from one place to the other? What is the least expensive way, to do some task? That kind of situation arises in real life a lot, right? So how do we solve that problem? That's the focus of our class today. So basically what we do is we change the given problem situation into mathematical equation or function. Okay, we extract all the information given in the problem situation, and then we come up with some model, some mathematical model, which we call functions or equation. And once we have the functions or equation, then we know how to find the maximum and minimum values. All right.
Okay.
So one thing that you need to know, the meaning of optimization. We discussed this in our last class. Optimization sometimes is minimum and sometimes maximum depending on the situation. Okay, so if we are given the profit function and if we want to optimize, that means you need to maximize it. And if we are given cost function and we want to optimize it, that means we need to minimize. And now what is the optimization? Well, it is the process of finding maxima or minima, and the functions we are optimizing is called the objective function. Okay, the function that we optimize is called the objective function. So the objective functions can be recognized by its word like greatest, least, highest, farthest, most. These are the keywords that you will see. That will help you to figure out which one is your objective functions. Okay, so in order to solve these real world problems on optimization, we will follow this three-step method. I want you to read these three steps. Step one, you need to read the problem carefully. Make sure you understand what is given and what is unknown. Okay. Then translate the English statement of the problem line by line to mathematics. If possible, sketch a diagram and label the various parts using the mathematical notation. And this step, I believe, is the hardest step. Okay, in my experience, students find it difficult to translate, to change English language into mathematical language. In other words, to figure out the mathematical model is kind of hardest step for most of the people. And once you come up with the functions or equation, then what you need to do is, well, in step two, you need to identify the objective functions and write the equations or formula for the objective function that is to be maximized or minimized. And once you have that objective functions, and what you need to do is use the calculus to find the optimum values. That means you take a derivative, find the critical points, and test for maxima or minima. So these are the 3 steps that we're going to follow, okay? Let's look at example 1. So here, problem situation is given. Step 1, read the problem carefully and understand. Sometimes you may need to read 2, 3, even 4 times. Okay, read the questions very carefully until you understand what is given and what you need to find. The manager of a garden store wants to build a 600 square foot rectangular enclosure on the store's parking lot in order to display some equipment. 3 sides of the enclosure will be built of redwood, as you can see in the figure, redwood fencing, and the redwood costs $7 per foot. But the 4th side will be built of cement block, the blue one, as you can see. This is the cement block. Okay, and this costs a little bit more. It costs $14 per foot. Okay, and find the dimension of the least costly such enclosure. That means we need to find the dimension of this rectangle that minimize the cost. Okay, so minimize the cost. Your objective is to minimize the cost. That is your objective function. So your objective function, so step 1, read the questions carefully. Yes, we read it. And then if possible, sketch the diagram. Yes, we sketch the diagram. And label the various parts. Yes, we label it. It is X, X, Y, and Y. That's how we label it. Okay. Step 1, we did all of these. We read it, we understand, we sketch the diagram, we use mathematical symbol and notation. Step 2, identify the objective function. So you're, okay, let me write the given information as well. What is given here is that we want to build a 600 square foot rectangular enclosure. That means area of the rectangle A, which is, we know that it is X and Y, X times Y is given to be 600 square foot, okay, feet square. So this is given, I listed that down. Step 2, write the objective function, okay, objective function. What is your objective function? What is your objective? What is your goal? To minimize the cost. That means cost will be the objective function. What is the total cost? Let's say total cost is this side, you know, the block, cement block costs $14 and all the other 3 sides cost $7. Okay, so if it costs $14 for 1 foot and this one is Y feet, so the total cost to make this cement block side is 14Y plus this side right here, this side cost $7 per foot and the length is X feet, therefore it will be 7X. In the same manner, it will be 7Y and 7X again. So the total will be 21Y plus 14X. Okay, that is your objective function. Now remember, in this objective function, there are 2 variables, X and Y, and we don't want that. Okay, we want to, the more variable you have, the problem will be more complicated. So somehow using the information given, if we can change it into 1 variable, then we can, you know, our life will be easy. Okay, so let us change it into 1 variable. How can we do that? Well, as you can see from here, I can write Y equals 600 divided by X. Let me say that this is equation 1. Now, substituting the value of y, we get cost function equals 21y. Y means 600 x power -1 plus 14x. So now you see that this is the function of one variable. Okay, so I can write c of x is this. Objective function is done. Now step 3. Let's go back. In step 3, use calculus to find the optimum values. You see, optimum value means take derivative, find critical points, and test for maxima and minima. So this is basically what we have been doing so far in this in the previous chapter. So we find the derivative. So let us find the derivative, which gives me negative 21 times 600 is going to be 126 and 20, because 21 times 6 is 126 over 20, and x -2. Okay, so that's and then plus 14. So that's going to give me negative 126.00 over x squared plus 14. So that's going to give me negative 126.00 plus 14x squared over x squared. So this is my derivative. Now for critical number, let me go this side here. Okay, I'll go from here to there. So for critical number, we know that the derivative equal to 0 or the derivative is undefined. Right? So this means 0 means this negative 126.00 plus 14x squared equal to 0, and this side 0 is x squared equal to 0. This gives me x equal to 0. But this is not in the domain, because if x equal to 0, there will be no questions of rectangle. I mean, the rectangle doesn't exist. Okay, so not in the domain. Or impossible, you can write. And from this one, solving this, you're going to get x squared equals 126.00 divided by 14. So x equals positive and negative 30. Is that right, guys? Notice that x is the length of the rectangular field, so it cannot be negative. Okay, since x is length of the field, it cannot be negative. So x equals to 30 is the critical number. So critical number is x equals 30, 1b. Now the question is, we know that the maximum or minimum value occurs at x equals to 30, but we don't know whether it's maximum or minimum. Now we need to test. To test maximum or minimum, you can use first derivative test or second derivative test. Remember, first derivative, if you want to use first derivative test, you need to draw a number line, put 30 there, and then we have two intervals and choose the testing point for each interval and you test. But here I'm going to use the second derivative test because that makes life easy. Okay, it's I think it's less time consuming. So to test maximum or minimum, we use second derivative test. Remember, you can use first derivative test if you like. All right, so second derivative means, let me just find the second derivative. My first derivative is, let me just copy that first derivative, okay? Let me copy the first derivative, which is, it was 14 minus, no, negative 126x negative 2 plus 14. That was the first derivative. So your second derivative is going to be, oh, there is 20, okay? So the second derivative is going to be 126 times 2 will be 252. Negative and negative will be positive. 0, 0, x power negative 3 plus 0. I don't have to write that 0. Or if I want, I can write this in a nice way, over x cubed. So that's what I got. Now, when x equal to 30, your second derivative is going to be 25200 over 30 cubed. Clearly, this is positive, right? There is no negative sign. It must be positive. So if the second derivative is positive, that means concave up. That means the shape of the graph will be like this, concave up. So in this case, you have minimum, right? So minimum. And this will be your absolute minimum, because when there is only one point, only one critical number, then the relative minimum or absolute minimum will be the same. So what we found out is that absolute minimum, or you can say relative, doesn't matter, both relative or absolute minimum at x equals 30, and absolute minimum value is, minimum cost is, you can find minimum cost. Even though the question doesn't tell us to find the absolute minimum cost, it just tells us find the dimension, which means the value of x and y, but we want to find the minimum cost just for fun, okay? So you just find c of 30, and that's going to give you the function c of x. Okay, let me just copy the cost function, which is 14x plus 21y is the cost function. Or maybe y we change it into, let me go all the way back. So the cost function is in terms of x. Okay, it is 21 times 226. Okay, this is the cost function. Or you can just, anyway, you can calculate this. I leave it to you. Cost function is 14x plus 126 x power negative 1. That is the cost function. So if I plug in the value there, I'm going to get 14 times 30 plus 126, 12,600 divided by x means 30, and that's going to give me, so this is $840. And now the dimension. So the dimension is for minimum cost, dimension of the rectangular field are x equals 30 and y equals y is 600 divided by x, which means 600 divided by 30, that means 20. Don't forget to write the unit, okay? This x is in feet and y also is in feet. So 30 feet and 20 feet will be the dimension that will minimize the cost. So we'll continue this later. If you have any question, please let me know. Okay, remember, we're going to use three-step method. And here is another example. Let's try this just for fun, okay? You need to read the questions very carefully and try to understand the question. That's extremely important. If you don't understand the question in one reading, then you can, try to do 2 reading or sometimes 3 or 4. That's fine. But once you understand and sketch the diagram and use the mathematical symbol to denote the given information, and that's step 1. From a thin piece of cardboard, 8 centimeter by 8 centimeter, square corners are cut out so that the sides can be folded up to make a box. What dimensions will yield or give a box of maximum volume? And what is the maximum volume? Let's draw the diagram according to the information given in example 2. I believe you have already drawn the diagram, and check your diagram whether your diagram is like this. Remember, we are given a cardboard of 8 centimeter by 8 centimeter. Okay, this is a cardboard, a square cardboard. And the question tells us that you cut out some corner. You cut out this part, you cut out this, cut out that, cut out this part, you cut out that. And then if you cut out this part, then this remaining part here would be 8 minus 2x. If the whole length of the cardboard is x, the whole length of the cardboard is 8 centimeter, and if you cut out x centimeter there, then x centimeter this side, so the remaining, the middle part here is 8 minus 2x. Okay, same thing here. It will also be 8 minus 2x, this part. Now you fold the sides. So when you fold the sides, you will get these kind of box. Okay, the box will be of this, like this, of this kind. So one side here is 8 minus 2x, another side is 8 minus 2x, and this height of the box will be x. Does that make sense? Now we want to cut out the cardboard such that the volume of the box will be maximum. We want to maximize the volume. Remember, our objective, our goal here is to maximize the volume of the box. Therefore, our objective functions will be the volume of the box. Now, can somebody tell me what is the volume of the box here? Well, you know that the volume of the box will be L times B times H, and this is your L, this is your B, and this is your H, right? So LBH, that is your volume. Okay, now let me just write it down here. So step 1 is done. So what is given? Well, it's 8 centimeter. So let the square corner that is cut out equals x centimeter. Then the length of the box, then the dimension of the box, dimension of the box is given by L equals 8 minus 2x, B equals 8 minus 2x, and H equals x, all centimeter. Okay, that is given. And now step 2. This is your step 1. Step 2, you need to find what is the objective function. Okay, what is your goal? Objective function will be minimize cost. Minimize cost. No, sorry, maximize the volume. So the goal here is maximize the volume. Sorry, guys. Maximize volume. Now the formula for the volume is, so volume of the box V is given by L, B, and H. We know that. L is 8 minus 2x, 8 minus 2x, and x. So that's going to give me okay, so this will be 8 minus 2x, 8 minus 2x, which will be 8 minus 2x whole square. Using a minus b whole square formula, you're going to get 64 minus 32x plus 4x square, and you multiply that with x. So the final term will be 4x cubed minus 32x square plus 64x. So now the volume B, our objective function is, let me just copy here nicely, 4x cubed minus 32x square plus 64x. The good news is that this is just a function of one variable. Remember in the earlier case, in example 1, we had 2 variables, so we had to change that y into x, right? We need to change it into one variable. But in this case, the good news is we have only one variable. Now, objective function is this. All we need to do is we need to find the critical points and then test whether it max, which value is maximum. That's all we need to do. Step 3. Now find the derivative, which gives me 12x squared minus 64x plus 64. Guys, I think you can do it by yourself. Take a couple of minutes and try to complete the rest by yourself, okay? Okay, so now we have the derivative and we need to find the critical point. So for critical number, or critical point, we know that this derivative equal to 0 because there is no denominator. Simply you can write that. So which means 12x squared minus 64x plus 64 equal to 0. And then if you can take 4 common, okay, once you take 4 common, so that's going to give me 3x squared minus 16x plus 16 equal to 0. And so if you simplify it, you're gonna get x minus 4. If you factorize it, you're gonna get x minus 4, 3x minus 4 equal to 0. So this gives me x equals to 4 and 3x equals to Okay, x equals to 4 over 3. So we got the two values here for x. Now remember, this one is not in the domain. X equals to 4 is not in domain because you see in this cardboard the total length is 8 centimeter. If you just cut right in the middle at 4 centimeter, then you don't have anything to fold on. Okay, so you cannot make the box out of it. If you cut right in the middle, you cannot make a box. That is not in the domain. So this is the only possible value for maxima or minima. Now we know the critical number. Okay, so the critical point is, critical point x equals 4 over 3. We know the critical point, but we don't know whether it is maximum or minimum. All we need to do is now to test maxima or minima. You can use first or second derivative. So we use second derivative to make life easy. Okay, second derivative test. So that means my second derivative will be, so the first derivative is 12x squared, second derivative will be 24x minus 64. And when x equals 4 over 3, your second derivative is going to be, all we need to do is we need to test that point x equals 4 over 3 into the second derivative, and that's going to give me 24. X means 4 over 3 minus 64, and clearly this is negative, right? It is negative. So if it is negative, second derivative negative means we know that this is concave down. So concave down means the shape of the graph is like this. So this means we have maximum. Okay, so maximum, we got that. What we know is that the volume is maximized, so the volume is maximized when x equals 4 over 3. Any questions so far? In these questions, we were told we are required to find the dimension of the box as well as volume of the box. Two things, okay? Look at the question. The question is this: what dimension will give a box of maximum volume, and what is the maximum volume? So we need to find both. Now, dimension means LBH. So the volume is maximized when x equals 4 over 3. And so the dimensions are L equals 8 minus 2x, B equals 8 minus 2x, H equals x. So that means 8 minus 2 times 4 over 3. This is also 8 minus 2 times 4 over 3. And this one is 4 over 3. So this guy will be so this will be 16 over 3. This is also 16 over 3. This is 4 over 3. And now the volume is, so to find the volume, you can simply do L, B, and H, or you can substitute the value of x into the volume function. I think this one will make life easy, okay? Instead of substituting this, because, you know, this is one way is to do this, LBH, because we know the volume of a box is L times B times H, which means 16 over 3 times 16 over 3 times 4 over 3. And that's gonna give me I'll leave it to you. And if you want, you can do alternatively. You can find volume is, let me just copy that. So the equation is 4x cubed minus 32x squared plus 64x is the volume. And when x equals to 4/3, you can substitute that 4/3 cubed minus 32 4/3 square plus 64 times 4/3. And whatever you get should be your answer. So when you work it out, then the volume is going to be 37.9 approximately centimeter cube. Okay, in this case also you can find that will be 37.9 centimeter cube.